Okay, I think it's almost time to start. Tommy, are you ready?
Yes, it's okay. Yeah.
Okay, so maybe good afternoon, everybody. Welcome to the Asian Pacific Analysis and PDE seminar. Today, we are very happy to have Professor Congming Li from Shanghai Jiaotong University. He will give a talk on classifications of solutions to some linear PDEs of elliptic type and their applications. Before we start, let me say a few words about Professor Li. Professor Li graduated from NYU in 1989 under the supervision of Professor Louis Nuremberg. And then he went to UPenn as postdoctor, and then went to University of Colorado and got to be a full professor there until early of the century. He moved to Shanghai Jiaotong University. Now he's a chair professor at Shanghai Jiaotong University, and also he's a fellow of AMS. Professor Li has been an expert in the field of linear elliptic equations and applications. He's done many interesting work, and so many important work on linear elliptic equations. So today we are very happy to have him to give us the Analysis and PDE seminar. So, Congming, please start. Yeah.
Thanks a lot for the invitation to speak at the Asia Pacific Analysis and PDE seminar, and I feel very happy to talk a little bit about some of my work and introduce some method in the nonlinear PDE analysis. And of course, thanks the organizers, especially Professor Xin, for introducing me and for inviting me to be here. Okay, so now let's. I didn't go to much details of the method, which I should, and also some of the work this mainly as also my research. Most of the work are centered around the method moving planes. Okay, and it is studying the structure of solutions or symmetry of solutions, and it was originally introduced by Alexandrov in the study of the geometric PDE problems, and then being used by Sarin for the overdetermined PDE problem, and then the PDE method moving planes, first studied the to show a solution on the ball non-negative solution with zero boundary should be radially symmetric. This is by Nuremberg, and classification of very important blow-up equations. They also did this, but with some conditions to remove certain kind of decay condition or some kind of artificial restrictions. Caffarelli, Gidas, Sprague made some very fundamental contributions, and we also did some work. Okay, so let me go to these things. Okay, so briefly I will introduce the problems and the a priori estimate, the blow-up method. Probably many people are quite familiar with it. And then later on, recently we have been focusing on the fractional Laplacian, which is also pretty interesting, and I will present something maybe I think is interesting. Then we gave two examples of the Liouville problems, and in the middle we say how are the method moving planes are being, what is it? How do we use it? And some basic things about it. Okay, and then because of the importance, the method moving planes is basically a method that's using, applying the maximum principles continuously, and often we need various types of maximum principles. And here I present a proof, that we need to use. It is needed to study the whole space problem. Okay, and I present one proof for with a maximum principle for solutions on a punctured ball. That the solution has singularity at one point. Okay. Okay, for the problems we studied early on are the curvature problem. Usually the R, is a curvature. What kind of curvature can be prescribed on SN, and so usually the problem study are using the a priori estimate, degree theory, and the variation method. Usually we found where they can blow up and how do they blow up. Okay, so and then generally we can study the equations like this, and to the blow up, to say, oh, you don't have blow ups. However, problem one, we know it has blow ups. Okay. Okay. Say to explain the blow up method with Liouville-Tapp theorem. Liouville-Tapp theorem usually say, okay, your problem has only trivial solution. Okay. So now let's say, if I want to prove the problem 3, okay, the problem 3 to the solution has a uniform bound. Okay. Once you have uniform bounds, then the solution will have high order regularities lifted, say alpha order plus the order R you have. Okay, because you are lifting alpha order, so whatever you have, it being lifted up, unless the P is very small. But here P is bigger than 1, so usually it is good. But if P is for example, P is 1.5, then you probably can only lift one derivative, because U 1.5 is still differentiable. Okay, so things like this, because at the boundary you might have a problem. Okay, of course at the so this source term, flux, whatever the order you have, once you have the boundedness, you lift it up to be the alpha order of smoothness. Okay, so if alpha equal to 2, that's the regular Laplace, you always lift it up to be C2 plus something, and then go back. In there U is better and maybe I is very good, then you can go get C infinity, or if P is integer, right? So these type of things. So basically, for many elliptic problem, we know the thing is to get a basic, break up estimate. Once you break the barrier of scaling, usually you can keep lifting it up to be better and better. Okay, so that's the thing. So I think also because the another type problem we study is also the the Navier-Stokes equation. Is the same thing. Once you get the regularity beyond the LPQ, okay, say L3 infinity, bounded in L3 or better, then you can have higher order. Okay, or it's H1/2 is even better in R3, or I'm talking about R3. So similar thing, and therefore you just say, oh, can I break the basic level? Okay. This type of estimate, if we remember, the Ambrosati and Brizis, Lyons, they also did the work for the alpha equal to 2 case, and when P is the so-called critical case, once it's H1 solution, then you can lift it up. but the scaling is just barely there, and that's the critical case. Okay, so there are many different ways to get the a priori estimate. Okay, so here is a simple way. This is for P is less than critical. Okay, for P equal to critical, the treatment and the requirement is very different. Okay, okay. And here's the problem, though. We need to know that it requires much less than up to the boundary. Okay, okay. So here it's also important to know that the Rx is bounded from below. For example, if Rx equal to 0, everything equals 0, later I will show you some very bad situation, things can be bad. Okay. So, we want to prove it's uniform bounded. Now, then we say, okay, we are showing that bounded solutions are uniform bounded. Okay, this problem is looking at in fact, it should be bounded solution. Okay, so let's look at each one. Okay, so if you have sequence of unbounded, the solution that bounds goes to infinity. So the maximum, if a non-negative solution, we only need to look at the upper bound. Okay, goes to infinity. Then we scale it. So make it the maximum to be 1. Okay, okay, and everywhere is less or equal to 1. And the scaling with a suitable choice of scaling factor, so that this side is also at the maximum is 1, and at other places it's bounded. Okay, that's the basic way. And then you see the blow up point. Okay, xk is the maximum point, is the so-called blow up point. It goes to infinity, and we will see where it is. Okay, and to consider 3 situations. Okay, one situation is relatively far away from the boundary. Okay, therefore, center that this xk, your domain being scaling to the whole space, and you get a problem in the whole space, and we need to say, do we have a solution that's maximum is 1 at somewhere, and everywhere less or equal to 1? And you have the limit is because once you have this, and this is bounded, you have certain a priori estimate, so that VK converges, in every, locally, locally uniformly to V. Okay, some basic estimate you need, and you get this equation, and the Liouville-type theorem say, okay, we don't have such a solution, and therefore this case is impossible. Next, the blow up is very close to boundary, and because you are blowing up, so it become a half space. Okay, the domain, and you are inside. The blow up point is inside of the half space, and you have a half space Liouville-type problem. And then we still can, many problems we can prove you don't have such kind of solutions. Another, Liouville-type problem on half space. Okay, and the last case is impossible by the C2 alpha estimate. So, and all 3 cases impossible, and therefore you have, your assumption that MK goes to infinity is wrong. So you get a priori estimate. That's the basic method, and it is one way to, we are trying to say the classification is very important. Okay, Liouville-type theorem. And of course, Liouville-type theorem originally, Liouville-type theorem has 3 theorems: 1 in conformal geometry, 1 in dynamics, another in harmonic analysis. Okay. Okay, so that's the and a very interesting thing is that the it's being used for the to show the existence, for the, the so-called supercritical case. We for the hardy little the Sobolev systems, I will introduce it later. Type systems. If it's supercritical, then Bohozaev identity shows that unbounded ball you have no solutions, no non-trivial solution, and this non-existence, in fact, together with the shooting method, shows that you do have a solution in the whole space. Okay, so that's the thing. The shooting method, boundary map. You target. Shooting. You have a target map. That's one. Boundary map. Not that boundary map from the the geometry one. But this is the one that we learn in undergraduate in college. The boundary Dixon theorem. The existence of in an annulus kind of domain. How do you show the existence of a periodic solution in your shooting? You say that the solution from inside never go outside of the annulus type of domain. The directional field is always pointing inside, right? The boundary Dixon theorem. That's where we can use. Okay. And this kind of proof has many uses and many applications. So I think I just skip it. Okay. Now let me introduce you to the fractional Laplacian. Okay. Laplace, is s equal to 1, and with the typical Fourier transform. Okay, so the Fourier transform is just the psi minus Laplace Fourier transform is just 2 pi psi 2 squares, right? So with s power, we just s value, and this can be calculated for a very smooth function u. Is the principal value integration of this singular operator. Okay. This is a Cauchy principal value. Okay, like because your singularity is too big when y is close to x, so we do is cut off epsilon ball around x and integrate. Take epsilon goes to 0, the limit always exists. Okay. So because when you locally expand it, the linear term is just cancelled out. Okay, so and the quadratic term is bigger than 2s, so make this total power less than n, and it's integrable. Okay. And one can see that when x is very far away from the domain, and then this is 0, right? And uy only stay in a bounded ball because compact supported. And then for x very large, this is to the x n plus 2s power. So you have this estimate. And usually when we do this, we can distributional sense, so that we can define for more general functions. And to use test function, we want to say multiple with this that is integrable. Okay, that's why we introduce L2S, so that that is the next, this integral is this u is here, the u is not so good, but phi is C0 infinity. So this one is decays faster or than or similar to 1 over x to the n plus 2s, and u multiple with such a function is integrable. So this makes sense. So the Laplace SU acting on phi is defined like this, and so you can see it's continuous with respect to phi, and so Laplace SU is can be understood as a distribution. Okay, and it is well defined. So that's the, and of course, a distribution sometimes can be a function, right? You know, so when we say it is a function if this distribution on the domain is given by a locally integrable function. Okay, so we only need to test against all 5, compacts supported in a domain. If we say, usually we just say it's equal to f in omega. However, it's in the sense as a distribution. When it is in the sense of distribution, we say, oh, it's in this, okay, on omega, right? D prime omega. Okay, that's the way we define it. Okay. So, once U is locally smooth, then this formula holds in a domain. Okay, and this give you a C alpha function here. Okay, the fx is C alpha in omega in locally. Sorry. Okay, and so why we are interested in fractional Laplacian? Well, it captures a lot of non-local properties, things like we see I think in last century, a long time ago, 60s, 70s, and 80s, a series of papers in Nature, they studied that the virus and also the financial transformation. They did the test, okay, experiment, and they found out you can't use Laplacian to get the distribution of the how things distribute and expand to information to be learned to be communicated. Okay, and also later on it's in the population dynamics of virus or people or so, and they say, okay, we need non-local ones, because their order are different. Okay, and that's non-local one. It is associated with the Levy process, a kind of not the one, the standard one, the Brownian motion. Okay, even though Laplacian we should understand it better. I'm not quite familiar with this Brownian motion or Levy process, blah blah. But they are okay. There is such a physical science background. Okay, and to us also it's a very promising research field with many interesting mathematical problems to be solved, and as we said, many applications in life science. Okay. So let's consider the very basic linear problem. Okay, so Dirichlet problem. Well, for the Laplace, of course, boundary equal to 0 in certain sense, but U is locally good, inside is good, for example, but you need a certain, what do you mean? It's 0 on boundary, right? So, and because you are doing the fractional, and you need to be careful, for anything to be solved even in a boundary domain, this involves its value outside of the domain. Okay, the whole space should be defined, and of course we, as we, from the college we study since we separate them into different parts. 0 outside or non-zero outside, but f equal to 0, and we focus on this part. Okay. And here, there is a special solution that's outside is 0, everywhere, okay? And inside is non-zero, okay? And it is violated this condition, okay? And we ask this problem, what it is violating, okay? What's the problem we found? Okay, this equal to 0 is important condition, okay? If it is equal to 0, then, the solution must be 0, okay? But if C is non-zero, then this is non-zero. You can have non-zero solutions, okay? And, this kind of uniqueness, we need to study it, and, and that's one of our work, okay? And it seems the problem mainly is so to the boundary weight, to the boundary, okay? How fast it goes to 0. And we found, as we said, this condition is kind of optimal if and only if, okay? And, for the Laplace, it's also the same thing. If solution, uniqueness, you need this condition. Okay. And with this condition, you have a solution for any F, not too bad. Okay. LP theory you have. Okay. That's the typical W2P theory. F belong to LP, and then use W2P. Okay. So, I think my time is not that much. So let's jump to the similar result, just because, with the first order term, okay, you have to have S to be, Laplace, fractional Laplace need to be in control. So it should be order 1, S is bigger than half, Laplace is second order, 2 multiple S is bigger than 1. And you have, so it's all in the weighted space, okay? And you have the W2P theory almost, okay? In the ball, okay? Okay, so that's the study with an introduction to the fractional Laplacian. That's what is it, okay? Some basic things we can do. Okay. Now next we go to the some examples of Liu-Wei-Top theorems. Okay, that's the main results are obtained quite a few years ago, but many of the results are still played a many important role in many people's research. That's so we start with the Hardy-Littlewood Sobolev inequalities. This basically is Sobolev embedding. Okay, but Hardy-Littlewood, they did one dimension case, and Sobolev did the high dimension and some weighted ones, and E.M. Stein and West, they did completed the weighted space one. So now let's just focus on this system. If we want to say under this constraint, what's the best constant? Okay, the maximal of this, and Lieb proved the existence of the maximizer. And we studied the Euler-Lagrange equations, and this Euler-Lagrange equation is called Hardy-Littlewood Sobolev system. And of course, we can also once we have the Hardy-Littlewood Sobolev system, then you vary the the exponent, the growth rate, the P and Q. You can get you make it bigger, the super critical case. And when we make it smaller than the subcritical case, so we overall we call them Hardy-Littlewood Sobolev type systems. But this one, the critical one, from the Hardy-Littlewood Sobolev inequality, is called the Hardy-Littlewood Sobolev system. Okay. So this variable equation, if you take derivative about G, it's linear about G, so it's F acting on the integral with this, right? And if you take derivative about F, it's this acting on G. Okay, so this, this, for example, this one, and this you take derivative about F. is, f to the r's integral, so derivative is f to the r minus 1. Okay, so and let's use u to be fr to the minus 1. Then is the f to the r minus 1 equal to g over x minus 1, the integral. But g is just VQ, right? G is VQ. So G is VQ because you see you take the root of s minus 1 to the v to the 1 over s minus 1, which is q. Okay, so that's the how do we get the relationship between the usual one that we write for the Hardy-Littlewood Sobolev system in HLS system. Okay, and this system is corresponding to the integral systems, the differential systems. Okay, and well, for gamma equal to 2 or even numbers, this first one who proved that the equivalence, the two equation with the critical parabola. Okay, this is a critical condition. Okay, and let's give you the equivalence for gamma equal to even number which is integer type of Laplace. That's, I think, the complete proof was given by Juncheng Wei and Xinwang Xu, okay, in 1997, something like this. Okay, and then for the general case, for the gamma is less than 2. Fractional case, I think we did some and show the equivalence, and and Wenxuan and his group also did. The special case that P equal to Q, you can prove U must equal to V, and the equation reduced to a single equation, and these two equivalence was I think for the still we need some conditions. Okay, like U is belong to L, or some kind of space. That's a recent work is Dongming Cao and Wei Dai. Then we add from Beijing some university. Okay. Okay, the special, very special one is gamma equal to 2, and this is the blow-up equation that we mentioned earlier of the curvature equation, and the classification of 29 is, I said that's Gedasini-Nirenberg, they introduced the method of moving planes for the PDE to show the radial symmetry. They first did in 79 for the bounded domain, then this 81, and worked on this with the condition, with the decay assumption. And Gedasini-Sprague, Gedasini-Sprague removed this condition. Okay. And we then using Kelvin transform make it very simple. Okay. We and Xu did it for even integers. Okay. To classify the solutions. So then for the general one, okay, for the general one, and this is Elliott-Libb's open problem. Okay. He think they should be true, and we did. We proved this with the method of moving planes for all gamma value. Okay, I solve the problem, completely solve the problem. Okay, so and of course, in 2D, then the critical power n minus 2 is becomes 0. So this n plus 2 divided by n minus becomes infinity. So that's, we know that's the exponential case, okay, and it's also classified. So to classify this, the method involved is the method of moving planes, okay. Well, so how do we do the method of moving planes? We here, or this minus n is sub-index this, okay. And let's just introduce give you a basic introduction, okay. So what we do is doing the reflection, okay, in one direction, say x1 direction, in x1 direction, okay. Then we want to compare, say, with the t lambda to be the plane that x1 equal to lambda, okay, and the sigma lambda is on the left of the plane, okay, lambda is very negative, okay, and then we keep moving it to be increasing it to the center. Let's say, F have the structure condition around x1 equal to 0. Well, most of the case, for example, in this problem, the 33, or this problem, or the 30, it just not involved with x, so it's of course monotone in x1. Okay, so here we need the structure condition that it is monotone in x1 up to certain places, okay, to the center. Okay, if it's non-trivial, then you can prove it must be reflected, about this center. So what we do is that, well, we compare the value, with the t lambda, so x1 equal to lambda plane with the center. We compare the value of u on the symmetric point about t lambda, the two. Okay, one is the left, which goes to 0, smaller. One is in the right. It's supposed to be bigger, a little bit bigger, and we try to show w lambda is positive, non-negative. Okay, and then we try to see what's the equation. Okay, and here we use f is monotone increasing, x lambda is in the right. Okay, it's bigger. The x1 component, 2 lambda minus x1, is bigger than x1 because x1 is less than lambda. Okay, so then you can replace this with x. Okay, x, and you linearize it about u lambda. So here we need f to be ellipses about u lambda, and you get this and the coefficients. Very often, this coefficient is very important. Okay. Unbounded domain, as long as it is Lipschitz, we are done. We are okay, no problem. Okay, and that's the power of the method of moving planes. On unbounded domain, it's very important to deal with this. And originally, in Nirenberg's original paper, that's where the difficulty comes, why they need the asymptotic, so that they say, okay, the bad thing can never happen at the infinity. A very large place, it's always good. Okay, that's their way of solve the problem. But in our work is that, okay, as long as this goes to 0 faster than certain rate, okay, in 2D should be faster than 1 over x to the 3 power, and in 3D or higher, it's just 1 over x squared, with small coefficients. That's okay. Okay, so combined together, you have this inequality. In the whole space, you need this decay rate. Okay, and that's the, say x in here, x lambda is here. So when the lambda is very, very far away from boundary, and then, your Cx is very small, we have a theorem, we know on bounded domain, if your C is less than the first eigenvalue, your maximum principle hold. And in the unbounded domain, the same thing is that just we need say if your C is very small epsilon over x squared, then it holds maximum principle. So and then this maximum principle works. You can prove W lambda is bigger or equal to 0. That's the thing. We need say in far away, very negative place where the lambda is very, very negative. On this domain, because C is, you have certain asymptotics, you can use maximum principle. So when we say maximum principle, we need keep in mind of its relevance. When we can use it with some kind of auxiliary functions. Okay, and on the domain, when we very close to this boundary, the lambda very close to the boundary, and the domain is very narrow. When boundaries, we know that when boundary is very narrow, your first eigenvalue is the width of the domains 1 over the width squared, d squared, 1 over t squared. So it can go to infinity. And once you are uniformly elliptic and C is bounded, so you can always use maximum principle. Okay, for very far away, when you keep moving, then you need to say, okay, the balancing only happens near the boundary because you are, and also near this close to the plane, because where it's 0, when you change a little bit, you can have the negative happens. And when it's positive and it's continuous, so when you move a little bit, it's still in most of the places it keeps non-negative. So the balancing can only happen near the boundary and the sigma lambda's boundary. Okay. So that's the thing. Okay. So that's the basic introduction to the method of moving planes. And so when we did the work, the main thing is so what is we need the asymptotics, but in the even with the Gidas-Nirenberg the solution, they need to assume this, and we want to avoid it. When Cavalli, Gidas-Sprague, they avoid this. They use the so-called the measured version of moving planes, which involves many very hard analysis. And okay, and what we did is that we do the Kelvin transform, and with the Kelvin transform, it's you have a good point inside, and you make it to the infinity, and at the infinity you have certain asymptote just as you need for the moving planes, from Gidas-Nirenberg's work. Okay, we have asymptotic. However, when you do the Kelvin transform, the infinity is being inverted inside into a point, and therefore you have singular point inside the domain, and you need maximum principle near this place to avoid the breakdown of the method of moving planes. Okay, so that's the thing. Okay, and okay, so now next, so this kind of moving planes method, all these maximum principles, and so then for the fractional Laplacian, people doing it, the method moving planes classification or solution always use before our work is always use the extension method. So if you study the problem in Rn and you get them into the boundary problem for Rn plus 1, okay, certain kind of harmonic in the upper space Rn plus 1, and then your problem is as a boundary value on the, because those are the so-called extension method being worked a lot. And then we just say using the direct method, which is another paper with Wenxiu Chen and Yan Li. Okay, and where it's used, basically it's using this maximum principle, but they are presented as directly used to conclusions, not saying, oh, how do we calculate this? And this give us this best estimate. Just you see the delta, the narrow region, the region's width, and to the boundary, right? The bad point to the boundary, and when s equal to 1, this is a d to the -2 power, and this is exact with a little bit some other better terms, good terms to be used. Okay, very negative. Okay, so and that can be used to control, that so-called. From then on, many people are, and more direct and simpler. The direct method of moving planes. Okay. So, I said, technically, for many problems, we need to use a Kelvin transform, and where we get a singular point at certain point, say x0 equal to 0. Okay. Then we need a maximum principle. This is a basic way to say maximum principle. Here, because with W is just, it's all in the sense of a distribution. Okay, so therefore we, we can't say, on boundaries bigger or equal to something. So we say just in a bounded domain, in a region, it's in annulus is on your lower bound, and then you have the whole thing. So it does not go to 0 along certain point to the point. Okay, and this is basically if I have time, I will present a little bit of proof of this theorem. Okay. Okay, with this kind of work, we can do many Liouville theorems. Here is the recent Liouville type theorem for anti-symmetric systems. Okay, so if it usually many people are doing the lower bound half space is 0. We say it's a symmetric. Symmetric ones that the solution can be very smooth in the whole space. Okay, and in fact, people proved they are indeed smooth. Okay, and we gave the Liouville type theorem for the non-existence. Okay, I think my time is, and there are many. Well, because of anti-symmetric, so your domain can be lifted to be bigger, and therefore, and then when you are in the bigger space, okay, this is L2S plus 1, then you do have solutions for some cases, okay, and most of the cases still have no solution in the Liouville type theorem. Okay, and the proof for the maximum principle on a punctured ball, it's the basic proof is a Boucher theorem. Okay, once you see it's a solution outside of the 1 point. Okay, it's a the domain is -1 point. Therefore, your test function can only be supported in B1 minus 0. Therefore, your solution is around 0. Your test function around 0 is 0, right? So, and how do we get it to be the whole domain is what? On ball. And that's Boucher theorem. Okay, Boucher proved that for s equal to 1, that's the case. And Brizes-Lyons in 80s proved for higher, Boucher only usually did it for 2D and for harmonic f equal to 0. Okay, and then this f non-negative and general one, it's did more. Okay, and now this is the more general cases. Okay, so the Boucher theorem is this one is This is Boucher proved in 1903, and Brizis-Lyons is 1981. Okay, and I think I'm not going to give you the proof. So I think time is up. Okay, my talk is I should end it here. Thank you. Already 5 minutes. Okay. Zhouping.
Yeah. Thank you. Yeah, and it's okay. So I think we still have time for questions or remarks. Yeah. So any question or remark from the audience? Yeah, you can ask questions through the chat room or just raise your hand, whatever. Yeah. Okay, let me ask a question to me. So go back to the formula 35. Can you go back to the formula 35? Yeah.
Almost.
35. Yeah. Yeah.
Is that 35?
No. Go back a little bit more. Yeah. No, go back a little more. But
let me close this.
Formula 35.
Okay.
Yeah. So, so in this theorem that you have what is just W belongs to R twice? Do you have any restriction on S?
This S must be the same order with this. This has no S is bigger than 0, less than 1. Yeah.
0 is less than 1.
Fractional, yeah, fractional.
I see.
You know, with the first order, and I think we also later on I also have the general one with the first order derivative, then S need to be bigger than 1/2. Yeah.
But your assumption is that your W already being positive away, in a puncture ball, right?
Yes.
So then, what you are saying that actually these positive bonds can be kept just. Now I try to understand how do we compare your assumption?
W can go to 0 as X goes to X0.
Oh, because here you take this half R/2 ball away. That's a assumption, so, but then you can control all the way up to X0. Okay.
Yes, yeah. From a little bit outside, annulus around it, and then inside is also big. Yeah, that's the center thing. Yeah.
So can we use this kind of thing to do the estimate of the fundamental solution?
Yes.
Okay.
So it's bigger than some, right? In fact, the solution we got is a constant multiple of the fundamental solution plus harmonic part. Yeah.
Okay.
The proof is that Boucher theorem. Once you have 34, the equation part.
I see.
And W in fact is equal to a constant multiple with the delta function at 0. So let's consider the simple case A equal to 0, right? Then it's just the fundamental solution plus the harmonic one. Yeah.
Okay. So the only assumption on the A just a constant bounded above. A function bounded above. I see.
Yeah, bounded above, it's good enough. Yeah.
Okay. I see. Okay. Okay. Thank you. So, any other question or comments?
Zhouping, I have a question.
Oh yeah. Okay. Then you go ahead. Yeah.
So, do you have also some related results on the fractional P Laplacian?
The strong maximum of this type?
Yes, for instance. So
we don't have. we don't have this, but we do have the Hopf type lemma for the P Laplacian, fractional P Laplace. And in fact, Wenxiong Chen studied much more.
Okay.
We have, Wenxiong and I have 2 or 3 joint papers, but he continued working on this with quite a few people. Yeah.
Okay.
Sometimes I'm diverted to the fluid equations to get a rest. Yeah.
Okay.